Okay, so the good news here is that I'm done traveling for this semester as far as I know, so everything should be smoother from now on. A few things here. Homework 6 has not been posted yet. We will post it tonight. And we are going to post the project as well on Thursday next week. So there is a very important thing that you need to do between now and next week. Find your project partner, as the project is done in pairs. Unless you would like to do it alone, yes.
Do our partners have to be in the same lab as we are?
It will be incredibly convenient if they are. The project is much more free-formed than the labs were. The lab sessions, the TAs will be in the lab session for your convenience. They'll give you some guidance, but it's up to you to implement each of the phases. And there'll be 4 phases of the project. Some of them will be a week long, some of them will be 2 weeks long. Okay? It's convenient if you can work together with your project partner. But I've seen people who basically split up the work and somehow, do it over the phone or email or chats or whatever you like. But I do recommend human interaction with your project partners. And I'll talk about, most likely in the next lecture, I'll talk about the project. What we are going to do is we're going to do part of the video encoding engine, hardware for that. We didn't know what H.264 is. A few of you do. Anyone else? What is H.264? Where is it used? Hmm? Everywhere, pretty much. I mean, most cameras implement that nowadays. Okay. What does it consist of? Yeah, and before the compression scheme, there is something else. So it compresses pictures frame by frame, but it does something else too before it attempts to compress. It tries to reduce the amount of stuff that it tries to compress. How does it do that? No? Motion estimation. It only wants to compress the pixels that have moved. It does not feel like compressing the background if it is the same in a motion picture. If you're looking over here, if it is a still camera sitting over here, it's enough once to compress the background and just looks at the blinks of switch its eyes to compress the difference between that. So in order to do it, you need to have this motion estimation. That motion estimation is an interesting problem that has to be done through massaging data in the memory and so on. And lots of people implement some kind of a custom piece of logic to do that. And that's what we're not going to do the whole thing. Most motion estimation is a pretty complex thing, and people write PhD dissertations on that. We're just going to do one slice of that motion estimation. Okay? But it's something that, it's a substantial piece of work, so this is not trivial, but it's something that you can put on your resumes if you do it in the end. I designed a motion estimation engine for H.264, almost. Right? If you want to claim the whole thing, you're more than welcome to design the whole thing later. You would usually design it in like 150 type of class. Okay? So we're going to break it up into phases such that it's more tractable to do. But I'll keep you busy every week for the next approximately 6 weeks. And the amount of work will be varying from a few hours per week, possibly, in the last phase, will maybe 20 hours for 2 weeks. One thing, and I'll keep repeating this. I hate repeating myself, but this will be very important. Some of these are easy to do, and you can do it basically in the lab session. Maybe the first one you can do it during the lab session, 2 of you. But some phases are going to have 20 hours of work, or more, depending how your luck is, if you take the right step. Between the 2 of you, that's very manageable over a week or so. But if you try doing it a day before the deadline, it's not going to be good. Okay? So do stay on top of that. And I'm going to give you, so I decided to put, since we're not starting a project this week, we're going to start it next week. There is one homework to entertain you in between. And there'll be fewer homeworks after that. But you do still have to stay in shape for the next midterm and the final. So you have to keep up with the material. The material, which you'll find out, is much more naturally flowing going forward. And it will be very tied. What we're talking about is going to be very much tied to the project. So you'll hear it in the lecture, repeat it in discussions, work on that practically in the project. So should be able to solve problems. Make sense? What was covered last time was a little bit of a recap and a little bit of a new material on what is the CMOS logic. Did it go okay? Did Matt do a good job? Yeah. Better than I do that? Should send him every time? Okay, what are we going to do today is a follow-up on that. And this is a very, very important lecture. If you can try to understand it, it'll be very good. So ask me questions now. And then you just need a little bit of practice. There is a simple mechanism that is called the method of logical effort that allows us to design circuits to run fast. So we've been talking about the CMOS logic, and you've seen how do we size, for example, gates, right? When you have a NAND gate, how would you size these transistors? Such that you have, so we usually size them, nominal sizing would be equal to match the equivalent resistance of an inverter when it switches. So for 2 transistors in a stack to have the same equivalent resistance as an inverter of a unit width, or a width of a W, how wide do these 2 transistors should be? Twice the width. How about the PMOS transistors? How wide should they be to be equal to the unit-sized inverter in resistance to the unit-sized inverter? Unit-sized inverter's PMOS transistor has twice the width approximately of the NMOS transistor. So, well, since they're sitting in parallel and only one of them is typically switching, then they should be a width of 2. Now, doubling the width of these transistors, this is a tricky question, relatively high. Is it the right thing to do, or is it possibly an overkill? In order to match the output resistance, to match the equivalent resistance of these inverters, do you need to double the width? So, I mean, basic logic says yes, right? Because we can look at one equivalent transistor there that is twice as long. In order to have the same resistance, we should make it twice as wide. But something has changed the basic assumption about that resistance that changes that a little bit. What do you think? What do you think? I have two transistors in a stack. What happens to that, their degree of velocity saturation? Are they more or less velocity saturated than one transistor? A little less velocity saturated. They have a little bit less of a field across them. So if I have put two transistors of twice the width, they're a little bit, therefore, less velocity saturated. Is their current going to be equal to a single transistor of half of the nominal width? No, the current is going to be a little bit higher. It's going to be a little bit of an overkill. So in practice, if you open a standard cell library that people design, you'll find out that these transistors here are only approximately 1.5 times the width of an inverter. But, well, we'll let Rachel ask a question.
Why would the current be higher and not lower?
They're less velocity saturated. It allows them to have a little bit more of an on current for the same gate to source voltage.
Oh, so it's not because it's not because the VDS is smaller.
Well, the VDS would be a little bit smaller as well. And as a result of that, you would have a little bit less of a velocity saturation. But this is a hard tank. I mean, this is not something that we have studied, and our model does not account for that. So from now on, in order to, for any problem that we are dealing with, you're going to use double width for sizing a stack of transistors. In the project, you can explore more if you have time. Explore more optimal ways of sizing, okay? How do we estimate the delay going in the high to low transition at the output? What's the delay equal to? If B is equal to 1, if B1 has switched already, and input A is the last signal that is arriving, what is the equivalent RC network that is discharging this output capacitance? Well, we have two resistors and two capacitors in the path. Oh, the bottom capacitor won't matter. That's right. Why? Because input B has arrived and discharged it. So the equivalent capacitance here, equivalent RC delay, tau will be equal to CL times 2RN. Okay? That's the total capacitance hanging off this node. In reality, it would be its intrinsic capacitance plus the load capacitance. Okay. Let's look at the second case. What happens if the bottom transistor is the one that, bottom signal is the last one that arrives? The top one has arrived already. This signal was at VDD, right? There is a path to VDD up there. This internal capacitance then is through the top transistor connected to the output and is definitely charged to VDD. So this capacitor is charged to VDD. When this signal arrives, it needs to discharge both CL and Cint. So the equivalent network for discharging will be CL, RN, Cint, another RN, and ground. What is the tau here? Exactly, from the Elmore delay formula. So it is equal to 2. So, what is the capacitance that CL sees? What is the resistance to ground that CL sees? It is equal to 2Rn. So this is 2Rn CL plus, what is the resistance that C int sees? Just 1Rn plus Rn C int. Which delay is longer? This one or that one? When you are designing a high-speed circuit that you would like to operate at the highest frequency, where will you put the latest arriving signal? On top or on the bottom of the stack? On top. The other way to remember that, always the closest to the output. Okay? That's a very important rule. And it's very simple to remember, and you should implement it. Because otherwise you're just wasting time putting it on the bottom. So when you have a critical path, the signal that is arriving the last, you always put it on top of the stack. Make sense? Yes? Interesting question. Can I optimize this delay by tapering this line? Right? I mean, if my delay is equal to that, can I do better by making the bottom transistor wider and its resistance lower than the top one? Which capacitance? Seen? Well, that is correct. But let's ignore that for a second. Let's say that I somehow can manage that capacitance to be exactly as it is. This is an excellent question, and this is suggested in textbooks. In older textbooks, this was suggested as a great way to size transistor stacks. Make them, the bottom ones, in order to optimize this delay, make the bottom ones wider, and then a little less wide, and the top one to be the narrowest. You can still keep the resistance to be equivalent to an inverter, right? I mean, you're just not going to make each of them twice as wide. This one, the bottom one is going to be a little bit more than twice as wide. This one is going to be a little less than twice as wide than a transistor in an inverter. And this has been studied in textbooks and proposed to students to do. And then you try to do it, and it doesn't work. Why? So you got the idea, right? I mean, what can I do to minimize this delay, right? I can make this bottom Rn. Let me just use another piece of TP is equal to 0.7 times the tau, and tau is equal to Rn1 plus Rn2 times Cl plus Rn2 times C int. Which tells me that this is equal to 0.7 times Rn2 appears twice times Cl plus C int plus Rn1 in order to, if I have this constraint that Rn1 plus Rn2 has to be equal to the equivalence resistance of an inverter, right? I would like to, I can distribute Rn1 and Rn2 in any ways I want. I can make Rn1, I don't have to make each one of them exactly to be equal to a half, right, by doubling their widths. I can make this one a little bit less than a half and this one a little bit more than a half, or vice versa. So this equation indicates that I should make Rn2 a little bit less than a half. A little bit less than a half of the resistance, making it a little bit wider than Rn1, such that it contributes less, right? Oh no. Excellent. Excellent. My drawing has just disappeared, as you can imagine. I got a new computer, which is, I just need to load up all of this. I need to move into that, and that's something that I don't have time for. Where were we? Let me redraw this whole thing. They call this one Rn1 and this one Rn2. This was Cl and this was C int. When I'm doing 1 to 0 transition at the output, I'm trying to discharge this, and let me just put taus here. I'll find out that Rn2 appears twice, and it is equal to multiplies both C int and Cl, and Rn1 only appears once multiplying Cl. So it would make sense to reduce the Rn2 a little bit. Okay, but where is the catch there? That tells me that I should design this stack like this. This is my M4, and this would be my M3. I need to have M3 in the layout narrower than M4. In order to do that, I would have to implement it like this. I would have to jog the diffusion. Compared to that, if I just had a simple stack with uniform sizes, it would look like this. This would be M3, M4. What happens with this intrinsic stack node capacitance when I go from this to that? Does it stay the same? Is it reduced or increased? And that's what Rachel said. It gets increased. By how much? What is the design rule to space these two things? Uncontacted poly pitch. So what is approximately? You guys have practiced layout already. So what is the design rule there? Well, it's about 2 lambda. It's about equal to the width of the minimum length of the gate. What is the spacing here? Well, this has to be at least 2 lambda, and then how far away this jog has to be from the end of a transistor, by at least another 2 lambda. So this diffusion region has approximately grown in size by a factor of 2. So my intrinsic capacitance has doubled. Is that good or bad? Yes. No. So first of all, right, I did not cut the resistance to a half, right? I mean, here I just made it a little bit wider without ignoring, with keeping C intrinsic constant. You can run an optimization problem and find out when you're going to get the minimum here. You know, it will turn out to be, if you believe me, it'll turn out to be that R N2 should be a little bit less than a half of the inverter resistance, and Rn1 should be a little bit more than a half of the inverter resistance, okay? But together, they have to be equal to the inverter resistance to have a fair comparison. Now, when you do that, when you put in C int and re-optimize it, but the C int has intrinsic capacitance, has to be larger because the layout requires you. Layout rules require you to make it larger. Then you'll find out if you rerun that optimization problem, you can never run, never win. Because of the layout where you have to put this jog in. So unfortunately, those books from old times are wrong, because those people who found that as an interesting homework problem to optimize this whole thing forgot about the layout. There is a DRC that you have to follow in order to do that. Again, to their credit, at some old times, you could have done all kinds of things in layout. Not anymore. And we have seen trapezoidal transistors and things like those. Yeah. Yes. This was before my times. I've never seen a real trapezoidal transistor, and the first layouts I've seen were 2 micron. So this might have been before that. Okay. Any questions about this? But this was an excellent digression. Stimulated some discussion. And I can give this to you as a homework or as a next midterm problem or a final problem or whatever you like. Yeah, you don't like it, huh? You can blame it on him. Any questions? Okay, what we have learned is that we are going to have typically straight stacks. There'll be no tapering of the stack. And if you want to run fast, the last arriving signal goes on top. Critical path goes on top. That's it. You know, a few notes about formalizing this. I don't need to spend too much time on it. We can calculate the Elmore delay. We can form this RC network for any gate that we like. And we can calculate this Elmore delay formally. We have seen Elmore delay last time. Would you like me to recap it, or you understood it? The way how we calculate this. First of all, the delay from the input to the output of this network is this, and first order network? First order, is this going to be a straight exponential? Is the time response, if I put a step in here, is the output going to rise up exponentially? Not perfectly. Okay. I have 3 capacitors. What does that mean? Let's use simpler words. No poles. I have not talked about poles yet. Which order the network is? What is the order of this network? Third order network. Therefore, its time response is governed by a third order differential equation. Who knows how to solve a third order differential equation? I don't. Anybody? Does anybody know how to solve a third order differential equation? Oh, here is a guy. Here is a guy. Yes, there is Laplace transform, and you can solve this one. What will the solution be? Will it be exponential? Few exponentials. Yeah, or maybe an ellipsoidal if you're unlucky. Right? It depends on the luck. I mean, if you're real lucky, it's 3 exponentials. If you're not lucky, ellipsoidal integral. But how does that look like? How does the sum of 3 exponentials look like? There will be no rippling, though. That if we are lucky here. So this is a first order. It will look similar to a first order network, just not quite. It will be slightly distorted waveform. So what does Elmore delay do? Does it linearize it, or it approximates this delay of a multi-capacitor network that is higher order network with the delay of an equivalent first order network. How does it do that mathematically? How is the mechanics of that approximation done? It's a little bit hard I mean, the mechanism here is very simple. How do you do that? How do you, since you seem to know this, these Laplace stuff and higher order differential equations, how it is done? What does it do in Laplace transform? Yeah, that is the other way of saying what. Yeah. So it is essentially, it's something that is called the moment matching. So matches the moment of this third order system with the moment of a first order system such that the moments are equivalent. Anybody knows what a moment is? Yeah, somebody knew. Somebody's had that. I'm sure I've learned that somewhere in my calculus. But all right. Now, somebody has been talking about poles and stuff like that. Has anybody taken 140 here, or is anybody taking 140? How many? Oh, a lot of you. Okay, how do you do this thing? How do you make a third order system look like a first order system in 140? Or you haven't gotten there yet? You find a dominant pole, or how is that? How do you find a dominant pole? What is one of the common ways of finding a dominant pole? Open circuit time constants. Well, this is the exact same thing in the time domain of open circuit time constants. Anybody heard of open circuit time constants? Who is taking at this moment 140? Okay, hold on for another month and they're going to get to open circuit time constants. So this is the time domain version of open circuit time constants. Okay. And how do you find that? So this is an approximation, right? I mean, this thing does not have an exponential response to the step. What it has, if you're lucky, it's a sum of exponentials. If you're unlucky, it has an ellipsoidal solution of an ellipsoidal equation. And the way how we calculate that, how do you find that equivalent time constant, is for each capacitor, trace the path to the input, and total the resistance that it goes through. So the time constant associated with the capacitor C3 is equal to R3 plus R2 plus R1. Time constant associated with C2 is R2 plus R1. Time constant associated with C1 is R1. Okay? And add up all of those, all of these RC products from all capacitors. You can do this in a formal way. So here is what you have is R1 C1 plus R1 plus R2 C2 plus R1 plus R2 plus R3 C3. What's the time constant here? C1 times R1, you're always going to the input, plus C2 times R1 plus R2, because R2 is in the way as well. Are you sure? How do you know that? How do you know that? I'll leave that one for a second. Plus R1 plus R3. I wanted to confuse you here, but why is that? Why there is no R2 there? Those of you that have taken 140 before and heard of open circuit time constants, why there is no R2? Okay, so since you volunteered, so if you're looking at this circuit, so for some of you it's going to fly over your heads and it's going to come back in a month when you learn about it in 140. How many poles are in that network? Three. That's right. 3 capacitors, 3 poles. How many zeros? Three zeros. 2 are in infinity. C1 and C3 are in infinity and at infinity, and C2 is a finite. The C2 zero cancels a part of the pole, of the frequency response of the middle pole. So you take it out to match the moments. Okay, so those of you who know something about the analog design, zero from this capacitor is at infinity, at infinite frequency. There is a short on this path when the impedance of this guy is infinite. There is a 0 from this one. Those of you that have taken like 105 or 40, do you understand approximately what am I talking about? Zeros and poles? Yeah. So this 0 is at infinity, this 0 is at infinity. C2 has a finite 0. Where is it 0? C2R2. Okay. Okay, so you know too much now. So this 0 is C2R2. The frequency of the 0 is equal to the C2R2. Well, that 0 changes the frequency response of this whole network by canceling a part of the response of the pole. So a closer approximation is then C2 times R1 only. It does not see the R2. Tricky, huh? But you understand what the rule is to get that first moment matching. You are only considering resistors that are on the common path for the capacitor to the input and output to the input. Are you going to ask for your money back for 140? There is a few others that have been, I think, in 140 with me last year. Yes. That's right. I'm sorry. It's not probably, definitely. R1. Okay. You know how to do this then. Okay, now the next important topic is the method of logical effort. And here is a simple formulation. How do I construct the path that has logic path that consists of multiple logic gates that has the minimum delay? How would you go about that? So for example, I can design a decoder. And you will find out the decoder circuit. We'll spend some time on decoders, and you guys are going to be designing decoders as well. We'll find out that the decoder is a circuit that takes a number of inputs. Out of them only, it takes a binary word, and then only turns on, only one of its outputs are going to be equal to 1. So essentially, it presents a very large AND gate of something that is an address. So for example, if I feed an 8-bit address here, I should generate 200. In order to build 8 to 256 decoder, I should build parallel 256 AND gates that are 8 inputs wide. So here's how I can do that. Well, I can take one 8-input NAND and one inverter, okay? Because I cannot build AND gates straight in CMOS. I can take two 4-input NANDs and one 4-input, and one 2-input NOR, okay? I get that from De Morgan's rules, right? I'm trying to calculate to compute what is A0, A1, A2, A3, A4, A5, A6, A7 equal to. And I can say that it is equal to A0. I can double negate this. It'll be equal to A0, A1, A2, A3. Not, or A4, A5, A6, A7 not, and the NOR of both, where these are my A0, A1, A2, ... A7 inputs. Or I can break it up even further. I can use 2-input NANDs followed by 2-input NORs followed by another layer of 2-input NANDs. Which one of these is going to be the fastest implementation? This one? No. This one? Or that one? We don't know. How are you going to figure that out? Design every single one of them and simulate them? You don't need to do it 256 times. But how are you going to figure out which one of them is going to be the fastest? Logical effort. All right, very good. So we all agree here that the method of logical effort is going to identify the fastest one for us. Okay. So another thing that is relevant to the inverters is to the decoders. They typically drive large capacitive loads at the output because they're used for decoding the memory arrays. And when you're decoding the memory array, well, there is a lot of bits hanging off over there, and there is quite a bit of capacitance. So they have to drive large loads. So would you like to drive a load with a large logic gate, or with using a few inverters? Would you like, and how many of inverters would you like to have there? Again, methodological effort is going to figure this out for us. It's incredibly elegant thing, and it's, by looking at it, you'll find that it's a simple extension of the buffering problem that we've been talking about before. Do you remember this problem? If I'm given the ratio of CL over C1, the overall fan out that I have here, what should be the upsizing factor for each of these inverters? What would be the fan out, electrical fan out of each of these inverters to minimize the delay? No, not 3.6. I'm given if I have a fixed number of inverters. Nth root of CL over C1, meaning that the electrical fan out of each of these stages has to be equal. Okay? Or the ratio of the load capacitance to the input capacitance for the first stage has to be the same as the ratio of the load capacitance to the input capacitance of the second stage, and so on, saying that C2 over C1 has to be equal to C3 over C2, and so on, to CL over Cn. Each one of them should be driving the same fan out. How did you arrive to that result? Calculate the delay for the whole path. You had n unknowns. How do you minimize a function that has actually n minus 1 unknowns? Take partial derivatives. Hopefully you still remember how to take partial derivatives. Those are usually the easiest ones. Take partial derivatives. And what does the optimization say? All the partial derivatives are supposed to be equal. And then usually all of these optimization problems have a simple solution, a very easy solution. Something has to be equal. And it turns out that in this case, all the fan outs have to be equal. Okay? You can try it out yourself. If you don't believe me, it was done 2 weeks ago in class. Now, if you're given, what happens if this ratio of capacitances is 2, turns out to be 2? Do you have too few or too many stages? If the ratio of capacitances between each of the, you optimize this, and you find out that for your particular problem, the ratio upsizing factor, or ideal upsizing factor, ideal sizing factor for this inverter chain is 2. Each stage should be twice as big as the previous one. Does that mean, is that going to be the fastest possible buffer that you can design? No. Because the fastest possible buffer would be the one that has the ratio of approximately 4 in standard CMOS logic as we know it today. Tell me this. So if it turns out that this sizing factor from stage to stage is 2, do you have too many or too few stages? Too many. Because if you reduce the number of stages, the fan out per stage would go up. If the ratio of capacitances is 5, do you have too few or too many? You have too few. You should add. And you'll end up with a smaller total delay. Make sense? Okay. I would like to use similar reasoning here to pick one of these 3. And here is how we do it. Here is a simple formal derivation. And I'm not going to spend way too much time doing that. But if you recall, we have done this for an inverter. And for an inverter, we have found out that there is an equivalent resistance for a transistor in a transition that is equal to some proportionality 0.69 times the equivalent pull-down resistance times the intrinsic capacitance plus CL. Okay? And intrinsic capacitance is the one that is hanging off over here that consists of diffusion capacitances. What you'll find out here, well, that's some resistance here that is some resistance per square that is modulated by the sizing of, it gets bigger if the length is longer, and gets smaller if the width is wider. By sizing the transistor, we can make it larger or smaller. And then all what I've done here is I have multiplied and divided this whole thing by the width, and it stays as what we have up there. So this is resistance per unit width. It's equal to resistance per square times L time divided by W. And this CW is equal to the intrinsic capacitance of the NAND multiplied by its size. Okay. And the NAND's intrinsic capacitance is given by its topology, how many transistors are hanging off its output. Okay. Now I can take this whole thing and multiply it and divide it by CG NAND, as done in the following equation. I multiplied everything by CG NAND and then divided everything by CG NAND. Nothing has happened. Now, what I've found out here is what I've gotten almost to the expression that I've had for the inverter, if you compare this with what we have had with the inverter. And what we had here is, instead of CG NAND, we had a CG. What is the relationship between the input capacitance looking into either one of these two inputs compared to a simple unit-sized gate, unit-sized N transistor? Well, I see a total amount of capacitance that is equal to 4. What is, by the way, the total capacitance looking into a unit-sized inverter? It's 3. Size 2 to 1. Okay? So I can say, I can just basically plug in these numbers that I've had for an inverter, and I'll find out that this ratio of input capacitance of a NAND compared to the input capacitance of an inverter is 4/3. I see 4 transistors. A total gate capacitance equal to the 4 unit capacitance is compared to 3. So this time constant, I didn't say that yet. Okay. I got 4/3 is the multiplying factor in front of the delay. I didn't talk about that yet. I just tried to derive this first factor, this 4. So input capacitance ratio is equal to 4/3 compared to input capacitance ratio of the NAND, 2-input NAND to an inverter is equal to 4/3. We agree to that? And that's, by normalizing this whole thing, is going to come out in front of this delay. You can try to convince yourself if you don't believe this derivation that you have here. So there'll be a factor that is multiplying this inverter delay that is equal to 4/3 that is driving the output fan out. How about the intrinsic load? What's the total amount of capacitance that we have here? 6. What is it in the 3? So what does that mean? what's the overall self-loading factor of a NAND compared to an inverter? Twice. Okay? This is broken up over here into two factors. 4/3 times 3 over 2 is equal to 4 over 2, and it is 2. Fair enough? But I'll stick with this 4/3. What does this mean? This is a 4/3 is the parameter that multiplies the inverter delay that corresponds to output load. This tells me that inverter, or the NAND, two-input NAND, is 4/3 worse driver than an inverter when it tries to drive the load, right? It is going to have 4/3 larger delay when attempting to drive an output load. And it comes out straight of the ratio output capacitances of the input capacitances. How about a NOR, two-input NOR? Well, the sum of input capacitances is 5 compared to an inverter that has a sum of input capacitances of 3, and it is going to be 5/3 times worse driver than an inverter. Yes? What? This? This is correct, right? This, I was going to come back to that in a second. This is correct. It's 5/3 times 6/5 is equal to 2. And that's the ratio of output capacitances at this node. 1 plus 1 plus 4 is equal to 6 compared to 3. It's twice as much capacitance. What am I trying to say here is if my load goes up by a factor of x, the delay of an inverter is going to go up by a factor of incrementally, not by a factor. So if f goes up, the incremental delay that is of the inverter is going to go proportionally to that increment, because the proportionality factor is 1. What happens to when I drive that same load with a NOR? It goes 5.3 times up proportionally to that load. So that tells me that my NAND is 5/3 worse of a driver than an inverter. I said, what did I say? NOR? NAND, NOR. It's a NOR. Yeah, that's where it came from. Let's blame it on that. Make sense? I'll come back to intrinsic delays in a little bit. Because intrinsic delay is not something that really has anything with our ability to drive the output load. Is this proportionality times the fan out. Okay. Let's apply this to sizing this path. I would like to take this path and optimally size it to drive the load. I know what is my input capacitance. I know what is my load capacitance. How I'm going to size this to achieve the minimum delay? Well, I'll find what is my total delay. Is equal to the inverter times the gamma plus C ND plus over C inverter plus this equation that I have for a NAND that is 4/3 times blah, 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 NR ND and so on plus this 5/3 times this whole expression that I have for the NOR. This whole thing is going to be a, I'll take T inverter in front of this whole thing, and I'm going to have an equation that has two unknowns. I know what is my CL, and I know what is my C in. The unknowns are C and D and C and R. How I'm going because it went, I multiplied everything out. So I now got this intrinsic delay that is 2 times gamma. I have two unknowns, C and R and C and D. How am I going to find them? What should I do to find them? Take derivatives. Somebody said take derivatives. Which kind of derivatives? Two partial derivatives with respect to C and R and C and D, and equate them. Okay? Do I have to do that, or I already know the result? Do I have to do that do I have to spell this whole thing out for every part that I want to size? I mean, this is already a pretty big progress, right? I've written this whole thing formally, and this is fairly easy thing to get to solve. But do I already know the result, or I have to spell out this partial differential equation? What should be equal? Remember, when we run, anytime we run an optimization problem, something has to be equal. The ratio of what? It's some variables have to end up being equal. Ratio, yeah, but it is the ratio. That's right. So, which ratio? He said effective fan-out, equivalent fan-out. What is the equivalent fan-out? I've never mentioned the word. Have you ever heard me mention the word equivalent fan-out? Oh, yeah, this 4 terms times that has to be equal to that, and has to be equal to that. That's going to be it. Right, the fan-out, it's exact same thing as we had in the inverter buffer optimization problem, where this term had to be equal to that term, had to be equal to that term. It's the same thing. It looks like fan-outs, just these fan-outs got multiplied by a constant. And that constant is not sizing dependent. It is just the topology dependent. And that constant is called the logical effort. Yes? That's an interesting point. It's an excellent question. But so one thing, before I step into that, by doing this brain exercise, if I followed it, when I am trying to minimize the delay, do these intrinsic delays matter? When I find partial differential equations, they all drop out. So they do not affect the sizing. That's why I put it on the back burner for now. I'll come back to it. They do affect the overall delay. The overall delay, they're in there, but they do not affect the sizing. Okay, so the optimum here is exactly the same as we have had for the inverter chain optimization problem, with one change, that these ratios of capacitances or fan-outs are multiplied by a constant that is proportional to the gate topology. Now, your question was, do wires matter? We'll come back to wires. Okay? So I can formalize this now. If you believe, if you don't believe me, please go and run these partial differential equations at home. It's not very hard. basically what I'm going to find out when I look at any of these gates, I'll find out that this is the parasitic delay. It is called, in the terms of logical effort formalism, it is called a parasitic delay, or you'll sometimes hear me, or most of the time I'll call it intrinsic delay. That's it. This parameter here is called the logical effort. It is a constant that multiplies the delay of a gate. And this is the fan out. And I can say that the delay of any gate that we have is equal to is proportional to the inverter delay times this intrinsic delay as a ratio of the intrinsic delay of that gate compared to an inverter, plus some proportionality to the output fan out. And that proportionality factor is called the logical effort. Because the more complex the gate is, the more of an effort it takes to drive the load. Now, this derivation would have been even easier now if I used that formalism up front. You'll find out that what needs to be equal is logical effort times the fan out. The logical effort, few things to remember this formalism, because now in order to size this path, I mean, one of the most complex problems that you have to design, to learn in this class and to do as designers is to design something to minimize the delay, to meet the timing. Okay? You don't have to solve partial differential equations. You just run through the formalism of the logical effort to do it, and we're going to start practicing that. A logical effort is, by definition, is defined as the ratio of, the easiest way to do it, to calculate that is a ratio of capacitances of a gate to an inverter, where they're sized to deliver the same output current, to have the same equivalent resistance when driving the load. So, according to that definition, what is the gate that has the smallest logical effort? It's the inverter, the least complex gate. And by definition, logical effort of an inverter is equal to 1. Ratio of its gate capacitance to an inverter capacitance is 1. The more complex the gate is, the higher the logical effort. Okay? So, inverter has a logical effort of 1. 2-input NAND has a logical effort of 4/3. A NAND has a logical effort of 5/3. How about 3-input NAND? Somebody quickly said 2. Let's verify that. I don't have that fast of a brain. How should I size these 3? 3, 3, 3. These ones? 2, 2, 2. What's the input capacitance of each of these gates? And the logical effort? 5/3. Can you calculate the logical effort for any gate? Of course you can. But there'll be some trickier examples. it will go through. But it's not rocket science, is it? How about the intrinsic delay? What's the intrinsic delay of an inverter? Assuming the diffusion capacitance is the same as the input capacitance. The gamma is 1, with gamma equal to 1. What is the intrinsic delay of an inverter? Wait a second. It's the ratio. The way how you can find it is the ratio of the output capacitance to the ratio of the input capacitance of an inverter. So it has 3. Input capacitance is 3. So this is 1. Output capacitance here at the output node, ignoring the stack here, is 6. Inverter input capacitance 3. These 2. How about this one? 6 divided by 3. How about this one? 9 divided by 3. 3. Can you calculate the intrinsic delay of any gate? Yes. But it's not at the output node. It is not really shared here. Well, you have to still have 2 separate fingers over there. Again, these are approximate things. So this may not be exactly, intrinsic delay may not be exactly 2, maybe 1.9. But remember, what is important here? This does not affect your optimal sizing at all, because this is not a factor. It just affects the overall delay in the end. Okay. A few other things. So if I come up, after this, I'm going to come up with this sizing factor, how much the output capacitance should be bigger than the input capacitance, or how much the size gate should be bigger. The following gate, the succeeding gate, has to be larger than the previous one, and that gives you a size of 2, for example. What does this 2 mean? Well, if an inverter is supposed to be twice the size, that's very simple. It means that it should have half of the resistance of a nominal inverter, of a unit size inverter, and it should have twice the capacitance. For a gate, there are 2 possibilities, right? I can say that the gate capacitance is twice the size, or the resistance of the gate is a half. I'll give you different results for the opposite, because they're related to a logical effort. The resistance and the capacitance are related to a logical effort. Now, in these notes, I'm talking about the gate sizes. The book does the other thing in these notes. Keep that in mind. I cannot do this thinking. For me, the easiest thing is to sort out the capacitances and then figure out what are the appropriate resistances that you end up with. So the size 2 gate has twice the input capacitance of a unit inverter. Make sense? Okay. Now, not every single path that you're supposed to size is going to have everything lined up. All the gates, just single gates, and nothing is branching out. There is no fan out anywhere. Then you have to, for example, if you're trying to size this to minimize this delay, and this is the delay of your interest, there is some other path that is a little bit faster, so it is not as critical. The way how you do that is you'll have something that is called the branching factor. this drives this other path. And this other path scales up with the exact same factor as this one path, because it always should stay a little bit faster. But you need to account this branching factor for each gate as the ratio of the total capacitance that is being driven here by the capacitance that is off path. Oh, sorry, it's the total. And this is not correctly. For each gate, this would be C on path for each gate. So this is C on path. This is C off path. And the branching per gate is equal to the total capacitance divided by the useful capacitance that is being driven. You can look at it like the current coming out of this gate is being divided into two parts. One of it is driving the useful load. The other one is driving the side load. What matters is the one that is driving the useful load. So only a fraction of the total current is being used for driving that load. It's an easy thing to do. So I'm going to pause here, and we're going to run through a few examples in the beginning of next lecture. Yes? Questions? And branching effort, you can calculate per gate or per path, up to you. Yes? Okay, so Matt has, if you have your questionnaires, just hand them in to Matt. It depends. It doesn't matter. It's a branching effort is 1 here.
Yes, because this does not have an
yes, that's right. That's right.
Okay.
Exactly. And I do have an office hour today. I would like to meet some of you.